Hello, and thanks for using TickBoom. A student has sent through this question, which appears as part of the final question of the Baulkham Hills Mathematics Extension 2 Assessment Task number 1, which was largely about complex numbers. And this was from their assessment in 2017. So this was part C of a question that had 4 parts, and the question reads, in the following diagram, OABC and ODEF are squares. The vector OA and the vector OF represent the complex numbers Z and W respectively. M is the midpoint on the interval FA, and MO produced meets DC at N. And we have a picture of the diagram here. So part 1 says, show that the vector OM is equal to Z plus W on 2. Part 2 says, express the vector CD in terms of Z and W. And then part 3 says, hence or otherwise justify why NM, the interval NM, is perpendicular to the interval CD. So what I've done is I've just kind of drawn up a bit of a shell of this diagram. It's probably not perfectly to scale, but I think it'll do for our needs. So what we're told is this first square is A, B, C from the origin, O. And then the other square is O, F, E, D. And they're both squares, so I'll just note that. That means all the interior angles will be 90 degrees, and that's going to come in handy. We're told that the vector OA is the complex number Z, and the vector OF is the complex number W. We're then told about the interval AF, so I'll just put that in another colour, this interval here. And we're told that there's a midpoint, and if I just try and keep this to scale, it's maybe about here. There's a midpoint M, so this length and this length are the same. And if I draw this interval CD, what we're told is that the line from OM, it continues on through the origin to meet CD at what is called point N. So I think that's the key components of the diagram that we're concerned with. So part 1 of the question asks us to show that the vector OM is equal to Z plus W on 2. So I think how we can start thinking about this vector OM is to think of the 2 ways we can get there. So first of all, the vector OM could be achieved by going first to OF and then to FM. So it's vector OF plus vector FM. And alternatively, the vector OM you could achieve by going to OA and then to AM. Now, the other thing worth noting is that because these two, because M is the midpoint of AF, it means the vector FM and AM will have the same magnitude, just the opposite direction, because they're both coming to point M from opposite points. So we can say that the vector FM is equal to negative of the vector AM, with the negative just indicating that different direction. So from there, what we could say is we could make these two equal to each other, since they're both OM. So we can say vector OF plus vector FM is equal to vector OA plus vector AM. We can then replace this FM with a minus AM since they're equal. So OF minus AM is equal to OA plus AM. And then just doing some rearranging, we will get OF, and I'll bring over this OA, so minus OA, and I bring over the AM equals 2 vector AM. And since the vector OF is W, I can replace that with W, and the vector OA is Z, so I can replace that with Z, and that is equal to 2 of the vector AM. And I'll just turn over, but what we can do now is rearrange for AM, so we'll get the vector AM is equal to, and we just bring the 2 over, so W minus Z on 2. Alright, so now that we've got vector AM, we can now come back to our vector OM, which is what we're concerned about, and we could probably take this one, where we've got OA, which is Z, plus AM, which we've just derived, so say OM vector equals OA vector plus AM vector, which equals, so OA is Z, and AM is W minus Z on 2. So I can just bring the 2, and we'll get 2Z plus W minus Z on 2. 2Z minus Z is 1Z, so we get Z plus W on 2 as required. So that's part 1. For part 2, we're asked to find find vector CD in terms of Z and W. So if we come back to our diagram, I'll just write that out in terms of Z and W. So if we look at vector CD, we could say that vector OD is vector OC plus vector CD. So that's probably a good place to start. So vector OD is equal to vector OC plus vector CD. And then I'll just simply rearrange for the vector we care about. So therefore vector CD is equal to vector OD minus vector OC. Now, if we think about what vector OD is equal to, if we come back to our diagram, this vector OD is basically we're rotating 90 degrees in an anti-clockwise direction from the complex number W. So actually we can say vector OD is equal to I times the complex number W, because whenever you want to rotate 90 degrees anti-clockwise in the Argand plane, that's equivalent to multiplying by I. And hopefully that's something you've seen, but if not, a very simple way to think about this would just be to draw up a simple Argand diagram. So you've got your real and your imaginary. Now, the number 1, if we just think about simply the real number 1, if I plotted that there, and if I thought about the number I, the complex or the imaginary number I, just by itself, that would plot here in the Argand diagram. And so you notice to get from 1 to I, we've come anti-clockwise by exactly 90 degrees. So that kind of basic principle extends such that you could take any number, and if you multiply it just by I, you're effectively rotating 90 degrees anti-clockwise. And you can say the similar for negative I, except you're just rotating clockwise this time, 90 degrees. So using that idea, we can say OD is equal to IW, because we're rotating anti-clockwise. And we can also say OC is equal to z times negative I this time because we're rotating clockwise. So OC vector is equal to negative I times z. So putting all that together, we get the vector CD is equal to OD, which is IW, minus negative IZ, which equals IW plus IZ, which equals I, and I write this as Z plus W, because that's going to come in handy when we get to part 3. So that's part 2 done. We've got CD in terms of Z and W. Now for part 3, we're asked to show that the interval NM is perpendicular to the interval CD. So if we come back to our diagram, this interval here is perpendicular to this interval. Now, as a general way of showing that two lines are perpendicular, we can say that if the argument of, well, let's say vector CD minus the argument of vector NM, if the difference of those two arguments is equal to pi on 2, or in other words 90 degrees, or in theory 3 pi on 2, so coming all the way around here, then the two lines must be perpendicular. So if we can find the difference of these two arguments, then if we can see that it's equal to pi on 2 or 3 pi on 2, then we've got our proof. Now, if I start with arg of CD, arg of the vector CD is equal to the arg of CD we've just shown to be I Z plus W. I might turn over here, but what we can then say, the arg of vector CD, if it's equal to the arg of I Z plus W, that means it's equal to the arg of I plus the arg of Z plus W, and that's using the result that the argument of A times B, any two complex numbers multiplied, is the arg of A plus the arg of B. So that's how we can split that out, and that will come in handy. Now if we look at the arg of the vector NM, the first thing we can note is that the argument of this whole ray is going to be the same as the argument of OM, because they're on the same ray, so that their angle with the horizontal axis will be the same. So we can say that the arg of NM is equal to the arg of the vector OM, and that means that's the arg of Z plus W on 2, because in part 1 we found that OM is Z plus W on 2. And using this similar rule, we could say that's the arg of Z plus W plus the arg of a half, since Z plus W on 2 is the same as Z plus W times a half. Now the arg of a half is just 0, because a real number would lie on the horizontal axis, so it has no angle with that axis. So that means it's equal to, the arg of NM is simply equal to the arg of Z plus W. So now that we've got all those ingredients, we can conclude that the arg of the vector CD minus the arg of the vector NM is equal to the arg of I plus the arg of Z plus W, that's this bit, minus the arg of Z plus W. These two will cancel, so it's just the arg of I, and as we see, I by itself, the argument of that is pi on 2. And since we said at the beginning that if the difference of the arguments is pi on 2 or 3 pi on 2, then the two vectors are perpendicular. So therefore, NM is perpendicular to CD. So that's that question. I think, yeah, quite tricky. You really need to be quite comfortable with complex numbers as vectors to tackle this question. And just seeing that basically to get to a certain point using vector ideas, you just got to see, well, how do I get there? I can go from here to here or from here to here. When we were thinking about CD, it might be hard to think of CD by itself, but you can always just go, well, to get to D, I'll have to go to C, OC, then CD, and you kind of then rearrange. So I think the question could have been quite daunting when you look at this diagram and it looks like there's a lot going on. But actually, if you just work step by step through each part by itself was pretty manageable. So I think when you're faced with questions like this, you just need to try and slow down and think about things just one little step at a time, and hopefully you'll eventually get to where you need to get to. I mean, this question was guiding us. The reason it wanted us to show part 1 and part 2 is because we used both of those results to eventually work through part 3. So it was a nice question from that perspective. But hopefully that's all made sense, and tick boom.